Hello, good evening everyone. I welcome you all on the ninth live session of this course, which is taken by Professor Anandya Datta. The course name is Ultrafast Laser Spectroscopy, as we all know, and today we will be discussing the weekly assignment 8th. So let's wait for a few students to join and then we can start the discussion. So let us start the session now. We are approaching the end of the course and I hope you guys are following the course well. So in the assignment 8, the first question asks, type 1 phase matching is EEO, EEE, EOO and OOE. Okay. So the first thing regarding phase matching is, let me use the pen. Let me write the different types of phase matching which are available and then we can see which is the type 1. So for we have different pump, the signal, the idler, and here we can write the type. Okay. So in the first one, we have the pump, which is what which gets generated. And the signal and idler are the two wavelengths which we feed in. So if the pump has E and the signal and idler are O and O, O and O are the ordinary ray, E is the extraordinary ray, and this type of phase matching is dependent, the classification is dependent on the polarization. Okay, so if the signal and idler are horizontally polarized for say, and the pump is, so E and O, in the last session I had told you that E and O rays are have perpendicular polarizations to each other. So if O is 0 degree polarized, then E will be 90 degree, right? So in this type, in which signal and idler are same O and O 0 degree, and the pump which comes out has a polarization E, that type is called type 1. That is the type 1. So our question says type 1 phase matching is EO, EOO. So you will think it is this one because it says EOO, but no, this one will be the wrong answer because the type is read from this side. Like we will read from here to here. Idler is read first, idler, then signal, and then the pump. So type 1 will be OO and E. So for this question, the correct answer will be the D1, not the C. Okay, because we read the phase matching as idler, signal, and then the pump, OOE, because these two are the pump gets generated. So what gets generated is considered at the end, and signal in idler is O and O. Right? So let's see the other phase matching also. So the same thing here, I'm writing pump. This is signal. This is idler and this is the So the other types are, if I will write in this way only, idler first as we pronounce. So the other type will be if this is E, the signal is O, and the pump which gets generated is E. So this one is type 2. Okay, so these two, signal and idler, are perpendicularly polarized, and the pump which gets generated is perpendicular to signal, and or we can say it is parallel to the idler E. The other case can be, there can be many such combinations. So we have three variables, we can have 8 combinations like that. So next can be the EEO. So if you will exchange these two, signal and idler polarization, still you will get the pump as E. So this one is type 3. Type 3, or it's a part of, it's similar to type 2. So it is 2D. Or this one can, we can say as 2A. The next one can be, we have all three same, E, 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 or we can have all three as O, O and O. 0 degree polarized all. And this one can be, all can be 90 degree polarized. So the last time I told you that signal and idler will be perpendicularly polarized, signal and pump will be perpendicularly polarized. But this type of phase matching, this types of phase matching, it comes from the type of crystal which we choose. So if the crystal is positive, if it is negative, these E and O can get exchanged. So if we have all three same, then that is type 4 and 5. So this is type 4, this is type 5. Next can be the reverse of the first one which we have taken, that is these two are OO and this one is E. So we will read it from the idler side, it will be EOO, which was given in this third option, EOO. So this EOO type of phase matching, it is considered as type 6, or to B it is same, to B. See, it is OEE, it is EOO. So depending upon the crystal, whether it is positive or negative, these two can get exchanged. Or 3A. The next can be, what we have left is OEO and OEE. This is exactly the opposite of the first one. So it is type 8 this is type 8, or we can say it is 1. And this seventh one, type 7, and whose reverse is this, we can see this one and this one, just E and O are exchanged. So it is for differently positive or negative crystal. So it can be type 2A. Also we can see where is cursor? Yeah, this is type 2A, correct. So these are the different phase matching conditions. So our question was type 1 only. So type 1 is this. The only thing to take care here in this question was that we read the phase matching conditions with idler first, then signal, and then the polarization of idler first, then signal, and then the pump. So let me write here, if O, here O is equals to 0° polarization, E is equals to 90° polarization. Okay, so that was our first question. Let's see the next one. So the next question is, wavelengths of pump, signal and idler are usually in the order 1 less than 2 less than equal to 3, 1 equals to 2 is less than 3, 1 greater than 2 greater than equal to 3, 1 greater than 2 less than 3. So we have pump. Pump gets generated. So it has the largest energy. So it is like some frequency generation. We combine two photons to get a photon of higher energy, and the pump is that photon. The pump gets generated which has the largest energy, and the other two photons, the signal and the idler, we combine signal plus idler to give the pump. Okay, so in conventionally it is taken that the idler is smallest energy, and the signal is in between the pump and the idler, right? So if we classify them in the order of energy, for energy we will have pump greater than signal greater than idler, and in the question it is asked about the wavelength. So wavelength will be reverse of energy order because energy and wavelength are inversely related. So for wavelength, we will have pump least, then the signal, and then the idler. That's what asked in the question. We have pump as 1, signal as 2, and the idler as 3. So 1 less than 2 less than 3. So this one is the correct answer. Also the signal and the idler can be of the same wavelength. So what happens in this condition, when it is true, this part in this is true for second harmonic generation. What we do, suppose we say we feed two 800 nanometer pulses, not two pulses, we feed 800 nanometer pulse, and we get the second harmonic as the 400 nanometer, right? So here the signal and the idler, they have the same wavelength. One photon will be taken as the signal photon and one will be taken as the idler. So for second harmonic generation, the signal and the idler can be of the same wavelength. So that's why it's given as that the 2 can be less than equal to 3. But the pump, it cannot be equal to the pump. Then there is no point of second harmonic or the sum frequency, because if one if signal or idler is equal to the pump, then what are we generating? There is nothing to generate then, right? So 1 will be less than 2 will be less than equal to 3. So that's how we solve this question. Yeah. So let me write it in a nicer manner. Lambda pump, no, not less than equal to lambda signal lambda idler. Smallest wavelength, largest energy. This one is the least energy. Or the longest wave. Okay. So let's see the next question. The next question says, in topaz C, the function of white light is to act as pump, amplify signal, amplify pump, amplify idler. Now, this question is regarding the instrumentation part. So, let's discuss a little bit about the instrumentation of this optical parametric amplification, and then we can answer this question directly. So here I have kept this setup, schematic diagram of the setup. And first thing is, let me write here. So the pump which we feed in, the pump for topaz the pump is the output of regenerative amplifier. Okay, so here this part shows the pumping. The pump light which goes in here through this black part, which is showing, this is the red beam, this is the pump beam coming. It hits the mirror M1, then TM1, TM2, then this reflector, and then this one. These two also are mirror, and then this one, and then it goes in from BR2. So here the TM1, these TM1 and 2 are, it can be like steering mirror or tuning mirror. So these mirrors are used to change the different path length, and also they can be used to align the beam in the horizontal and the vertical direction. So these two are there, these are movable. So the output of the region comes from here, hits M1, goes in this direction, then it is reflected, and then it hits the mirror TM2, then again reflected, it hits this mirror BR1, then so these two are at different level. It is not crossing each other. The vertical heights of these two are different. Okay, so then it is coming from here, again reflected, and then this goes in the topaz C. Okay, now inside part of this topaz C is this one, this figure. So now we will discuss about this figure a bit. Let me copy paste it here. Let me keep this figure. It's nice to look the figure, and then we can discuss the instrumentation better. So let's start from here. So what we discussed here, that the output of the region goes in as the pump. So this one, from here the figure starts. So this part, so after this part the path is this. This red light which is entering is shown as this one, which hits this BS1. Now what is BS1 is beam splitter, normal beam splitter. So BS1, what it does, splits. It is a 80-20 kind of beam splitter. So 80% light is reflected. We write here reflects 80 to 20%. So the most amount of light is reflected in this path, the second path. So we are discussing now the first, the beam marked as 1, this one. This one is the input beam. Input which in our pump beam, right? Input pump beam. And from where this input pump beam came? It came from the output of the region amplifier. So after this in pump beam hits the BS1, it's a beam splitter. It will split the beam in two parts. So the 80% or 90% goes in this direction, is reflected, and only 10 or 20% is allowed to. So here I have written 20, it's 90. So and only 10% or 20% is transmitted. So BS1 reflects 80 to 90%, and remaining 10% or the 20% light is collected by these two relay lenses, L1 and L2. Relay lenses L1 and L2. So we will discuss about this path a bit later. Let's go straight. The input beam comes, it hits the beam splitter, then 80% is reflected in this direction and remaining 20% is transmitted, and the L1 and the L2 These are called relay lenses. So what relay lenses do, relay lenses L1 and L2. So here what is the work of relay lens is like, so if they have same focal length, if two lenses have same focal length, then what will happen if this is one lens and this is other. So suppose they have same focal length and a parallel beam comes. So it's a convex lens. So when a beam will hit it, it will be focused at a point. So it will be focused to a point, and since these two lenses have same focal length, this is the focal length of this one and this much only is the focal length of this other lens, and these two are kept at a distance such that their focal length matches each other. So this one is the focal length for this lens also and for this lens also. So after this, these two beams will diverge from this point and it will diverge and it will come like this. So for same convex lens, when a beam comes from the focal length of the lens, it goes parallel after the lens. So this beam came in, it got focused at this point F, let's say, and from this F point the beam got diverged out, and a, a beam which comes from the focus of the convex lens goes parallel. So these beams again become parallel. So we can think that what is the point, before also the beam was parallel only, and later after these two lenses also it is parallel. So what is the point of putting the extra set of optics here? But they have a role here. So what is their role? So this I discussed when the lenses have same focal length, but this scenario will change when they have different focal lengths. So let's check one case, different focal lengths. So this beam is this lens has a larger focal length. So a beam coming like this, and this is the focus point, has a larger focal length, and there is a one smaller lens here like this. This has the smaller focal length, but the distance between these two lenses will again be such that their focal lengths coincides at single point only, this point F. So this one is for F2 and this length is F1, and we can see F1 is greater than F2. So their focal lengths are different. Now again the same case, that a beam coming from the focus will get parallel after it hitting the convex lens. So it became parallel. But here one thing changed is, this is the ray. So here we have the beam which was this big. This is, for example, the beam spot. After going through these pair of lenses, the beam diameter got reduced. The beam diameter. So we we have packed the same energy in a smaller diameter beam. Okay. We could have used some iris or some aperture also to cut out the beam or to reduce the radius of the beam. But in that case, what will happen if we are cutting out that part using iris or aperture? The rest will be blocked, and that much energy we will be losing every time. So it is always like it's a good practice, and it is also used everywhere, that to change the diameter of the beam we use two relay lenses, and that's why they are called relay lenses. And the third case which can happen, the reverse one, if this one is of smaller focal length, and this length is of larger focal length, then the beam will be expanded. So this one is, here the first one is F1 is smaller than the F2. So here in this one, in this case, we have L1 is of bigger focal length than the L2 part. So why this happens? Why we are using this one? Because we need to reduce the beam size or the beam diameter, so that it will be helpful in the next set of optics. So that's why these L1 and L2 are the relay lenses, in which L1 is a lens of larger focal length. So now the next part will be, so we have discussed till now that the input pump beam comes, hits the beam splitter, and from here that 80% light is reflected and 20% is transmitted, and here there is a change in the beam diameter. And after that we have this DP1 and DP2. Now these are mirrors only, but let's write here. Sorry, these are DP1 and DP2. These are quartz plate, set of quartz plates. So these are quartz plate kept at approximately Brewster angle. Okay, now the Brewster angle, why? Because we need to maintain the polarization. And then why it is approximately? Because this angle can be changed a little bit, it can be tuned. So these DP1 and DP2, these quartz plates are for little angle tuning. It will be used later. And after this we have this A1. A1 is the aperture. Here this is the delay tool. So it can be used to produce a delay. The tilt of these plates can give a little delay to the beam. So it's a delay tool. Now where is delay 1 then? Delay 1 is this one, the mirror M2 and the M1. You see this, I'm putting my cursor here, this one. This is our delay 1, which is a pair of mirrors kept on a retroreflector. Now after this aperture, now again the aperture, after this aperture there is L3 lens, which L3 focuses the incoming beam after the aperture on this beam splitter. Now again we have a beam splitter, BS2. L3 L3 is the focusing length. Now L3's job is to focuses the beam which is coming through the aperture. It's a collimated beam. So L3 focuses that collimated beam on the for white light generation. Right, so here we reached up to here that L3 is the focusing lens which focuses the incoming beam from the aperture to this sapphire plate here, from where we get the white light. Now after L3 we have this beam splitter BS2. Now, BS2's job is to again uh, beam splitter, it will reflect some part and it will transmit some part. So BS2 again transmits 20% and reflects 80%, right? So from here, see, from this part we will go in this direction first and the reflected one we will see later. So after getting transmitted, what will be the intensity of this light? So it came from the here input, which was 100% was this much. So suppose I told that this one is 1 millijoule. So 1 millijoule, out of 1 millijoule, 80% get reflected here. So 20% vented. So that is 200 microjoules. 200 microjoule was here in this path. Now from here again 80% got reflected and 20% is transmitted. So 20%, then 20% which is transmitted will be the 40 microjoules. So we have very less energy which is transmitted here, and even after that we have VF, which is a variable filter. VF is the variable filter. So what is the job of VF? It's a filter, kind of ND filter we can say, which cuts out the optical density. So we don't want to pump in so much light. From 1 millijoule we came up to 40 microjoules using the beam splitters. Even if this much energy seems high, then we can use the variable filter to cut the amount of power which is going in. So next part is the this VF1 variable filter. So now this part, the third, which is mentioned as 3 here, the third part of the beam is the pump beam for the white light generation. That's why it is written WLG pump beam, white light generating pump beam. So now this pump beam for white light generation hits mirror M1, M2, which are kept on a retroreflector for the delay, we know, and then it hits the this one WLG RP1. So RP1 here, RP1 is a rotatable polarizer. RP1 is a rotatable polarizer, or because we need to maintain the polarization, that's why we have a polarization controlling optics here, and which is our RP1. After this, after checking the polarization and all, then the WLG pump beam hits the sapphire crystal kept here, which generates the white light. And here the white light has been shown in the blue color. This generated white light goes, and again it is collected by this lens L4. It's again a convex lens, and then it hits this part which is TD. Now TD is a kind of it's right here. TD is some kind of diffuser. So let's talk about TD a bit later. Now, so after what it does, we'll discuss later. So after this L4, the white light, so blue color now shows the white light. The white light hits this DM1, which is again a dichroic mirror, and from there it hits this. It goes through this aperture and hits the NC1. NC1 is our nonlinear crystal. Now let's see the part which is from here. So this beam splitter 2, which reflected 80% here, this light goes and hits the mirror M3. Now again M3, which is using this lens L5, it gets collimated and it hits the mirror M4, and again this dichroic mirror, and then these two mirrors M3 M4 makes this part of the pump. This is now pump light. The red one is the pump. So M3 and M4 makes the pump light collinear with the white light. So here we have these two are collinear, and then they hit the crystal NC1, which generates the signal. And these two beams hit the NC1 such that after coming out of the nonlinear crystal, the pump light is blocked, and we move along with the signal. So here the diffuser, what it does, it has high refractive index. So it brings chirp in the pulse, chirp in the white light, which is generated after the sapphire. So here we are adding chirp. Earlier we had talked about how to reduce chirp from the pulse, but here we are manually adding chirp in the pulse. Why? Because here chirp is a good thing, because suppose if this is white light, here this part is the red part, it is traveling faster, and here is the blue part which is lagging behind. In between we will have yellow and orange. So if this pump, which is this one, if the pump which it comes at this point, it will amplify the red part. If pump comes at this point, it will amplify the blue part. If the pump comes at this point, so the temporal at the time at which these two beam comes together, that part of the white light will get amplified. So that's why if they are chirped, if these wavelengths have different time delay, then it is easier to do this amplification. So that's why we bring chirp, and because of this only in this setup we are using so many lenses, because earlier we had said that lenses we should try to minimize the uses of lenses, and we should use mirrors, curved mirrors in the path, because as many as these transmitting optics are there in the path, we will have that much chirp in the pulse. So here we are still using so many because we have to add chirp. So it doesn't matter if we are using lenses or so that's why we are using lenses here. Okay. So this brings the, so that was the job of TD here, the diffuser here. It has high refractive index and then it brings chirp, due to which in the refractive index of the red and blue light. Refractive index difference means difference in the velocity. Here I will write chirp is inherently added, and in this case chirp is good or helpful. Okay, so now let's look at the path again. So the delay for the white light is produced by M1 and M2, and the delay for this one, the beam 4, the beam 4 which is reflected from the BS2, the delay for this one is produced by this delay, the tilting quartz plates DP1 and DP2. So DP1 and DP2, if they are tilted, they will create a delay for both the white light and the pump light. But if we want to create a delay for white light only, then we have this delay one, M1 and M2. So most of the delays are created using the M1 and M2 only, but for very fine tuning the delay, we use DP1 and DP2. So fine tuning the angles of this creates the finer delays. So next one is next after the LC1, the pump is thrown away or it is blocked here, and then we get the signal which is shown here in the yellow color. The signal goes here. Now this is the part 6 of the here. So here the pump and white light, these are not collinear. So what happens, that the pump can be blocked at this point, so that the pump can be dumped, because now we have generated the signal, we don't need pump anymore. But the pump can be dumped after MC1, and this generated signal, which is the part 6, The generated signal, which is shown in the yellow color here, it is in the direction of the white light. So the next thing is this signal, it hits the mirror M5, M6 here. Signal hits M5 and M6. And then again we have a relay lens L6 and L7 to collimate the signal. L6 and L7, and it is collimated and then is focused on the mirror, a dichroic mirror DM2. Now from this DM2, it's kind of short pass filter. So this one, it allows the smaller wavelength to travel through, but it reflects the larger wavelength. So here, let me write here that this DM2, after L6 and L7, it is passed through DM2, short pass filter. So here I would like to add a sentence, that is that so amplification of only one color is happening. So that's why we are not utilizing the whole spectrum. So that's why we do not care whether the pulse is chirped or not, and if it is chirped, it is good because we get all the colors more separated out, and then choosing one color will be easier. So that's why the chirp is not an issue in this kind of setup. Now we were discussing that signal, after getting generated from this nonlinear crystal 1, it goes, hits the mirror M5, then M6, and then it is again collimated using the relay lens pair L6 and L7, and is focused on the dichroic mirror 2, and then it gets transmitted from the dichroic mirror 2 and then hits NC2, which is nonlinear crystal 2. Now we have this signal generated. Now we have to amplify this signal more. So a moderate intensity gets generated after NC1. Now for amplifying, there is a second pair of crystal. There is second crystal here. Now we have one part of our pump beam still remaining in the setup, which is this part, the second, the amplified, the PA2, the post pre-amplifier pump beam. So this one. Now this what we remember is that after BS1, 80% light came through this. So that's why it is shown in thick red lines. That is, it has more of the optical density in this direction it came, and then we utilized very less power, only 20%, and then again we chopped off 20% at this here beam splitter 2. So we used very less power to generate the signal. Now we got a signal which has a moderate intensity. Now we have to amplify. For amplifying, we will use this remaining 80% of the input light, and then the second stage is happening when this input now we will focus the direction of the path of this beam which got reflected after BS1. So after BS1 it hits M7, then it goes to M8, it hits M9, then goes here straight, hits M10, 11, 12, and after that it hits the dichroic mirror. So in all this process, let me write the 80% beam So now we are looking at the path of this beam 2. It follows after BS1, it hits M7, M8, then goes in here M9, then goes straight to M10, then M11, then M12, and after that it hits the dichroic mirror 2. And from here it gets collimated, gets collinear with the signal. So after now this dichroic mirror, it's a short pass. So this one is, suppose we have 800 pump and signal is suppose 400. Then it won't allow to pass this because it's a short pass dichroic mirror. It will allow smaller wavelength to pass. So our pump gets reflected, and once it is reflected it becomes collinear with our signal which was generated at NC1. So this many number of mirrors was to align this, to check the path length, to make the alignment such that the pump beam has a collinear geometry with the signal. That's why we have to go through these many number of mirrors. So many mirrors to assure the alignment of okay. So we have to check on that, and we have to adjust the path traveled by the pump beam so that it, after hitting the dichroic mirror, its path is exactly collinear with the signal. Now this is the second stage at NC2. This is second stage amplification. First stage was at NC1. First stage was the generation of the signal. Now second stage is the amplification. Amplification is done. The generation was done using the it was not collinear, but for amplification we are using collinear geometry. Because at generation of the signal, we did not use collinear geometry because after that the pump light will also have to come, and again we'll have to use some kind of filter there to block that. But if we keep the geometry not collinear, then it can be dumped. It will go in a different direction and can be dumped there easily. Set a slide. So now what I have written is about these many mirrors from M7 to M12. We have this 6 mirrors. So why there are so many mirrors? These mirrors are to correct for the temporal overlap and to match the path length. Now after DM3, so after DM2, we the both the signal and the pump hits the nonlinear crystal, which amplifies the signal, and then it hits DM3. DM3 is again the short pass filter which allows the signal to pass through, but it blocks the pump, and then pump is reflected and it hits the M13 mirror, then M14, and then we can take out the pump also. So the last part of the setup, DM3, it gives amplified signal, and the remaining output which comes out, the remaining pump which comes out as the output pump beam, we can use it further that beam. So here it can be used to generate further second or third harmonics. So we see here this dichroic mirror, it amplifies the signal goes out, then the pump, since it is a short pass filter, the pump is reflected, it hits here, it is M13, it's not written over here, it is M13, this one is 13, M13, and then it is uh, reflected to M14, and after M14 it comes out as the output. Okay, so this pump beam, now it is again pump again, so we can use it next further, like here we can keep one more setup for second harmonic generation or third harmonic generation as we need. So that was the path or the whole instrumentation of the optical parametric amplifier, the topaz. Now let's come back. We have two questions regarding this, so let's discuss the questions now. This was the setup which I explained. Now the question 3, in the function of the white light is to act as pump to amplify signal, amplify pump, or amplify idler. Now Here, what is white light doing? It is basically uh, the white light is basically used to generate the signal. The pump, so here it is not written to generate the signal, so we can choose from white light, we can choose any color which we need to amplify. White light is generated just to have a wide range of color options available, wide wavelength range available. So we can choose any one of them to amplify. That's why we first generate the white light here using the sapphire crystal. So answer to this question should be to amplify signal. The white light is used to amplify the signal. So first amplification, white light also has signal. We could have used some kind of filter to get the signal, but that will be of very much less intensity. So first part of amplification is done here at NC1, and then it goes to NC2 to amplify more. So first one is NC1. So here first amplification. And here is the second amplification, 2 times amplification happening. So in topaz C, the function of white light is to amplify the signal. So the answer will be B. It is not acting as a pump because pump is this one. This light which goes in is the pump. This pump, from where we get this pump? We get this from the output of this regen amplifier. Here we have a regenerative amplifier which gives the output, this one pump, and we use this as the pump light. Amplify pump, no, we don't need to amplify pump is already amplified. Amplify idler, no, we are talking about in terms of signal here, not the idler. So the answer should be B only. Okay, so this was the instrumentation part, the topaz. Let's see the next question. Next question is also related to the amplification. In topaz C, most of the input laser beam is used for generation of signal in the first stage, generation of white light, amplification in the second stage, amplification of idler. Most of the input beam it is asking. So it is asking about the beam which we reflect at the first point, which gets reflected after the beam splitter. So you can see this is the most of the input beam going here, shown in thick red color. So this part of the beam, what it does, it is used for the second stage amplification. I have written over here second amplification. It does not go to generate the white light, not to amplify the signal at first. For first amplification, for first the generation of white light, we use the 20% of the 20% light, right? Then we amplify the signal using that, using 20% light. Then we get the signal with moderate intensity, moderate amplification, and then we at the nonlinear crystal 2, we use this 80% light to get higher amplifications. So most of the input beam, so the most of the input laser beam is used for amplification in the second stage, right? Which is 80% of input pump beam is used for second stage amplification. Generation of, first option says generation of signal in the first place. No, signal is generated using, let me write here, signal generation is happening using 20%, sorry, 80% of the 20%. Using 80% of 20% of input pump beam. And white light generation using okay. So if you write in this diagram, so here we suppose we give x. Now 80% of x comes in this way, 80% x, and 20% goes here. After this beam splitter 2, again 20% goes in this. So here 20% of 20% x goes here, and this part of the beam is 80% of 20% x. Okay, so this is what I wrote here. So I hope the question and the instrumentation of the topaz is clear now. Most of the input laser beam is used for amplification in the second stage and not elsewhere. So we spent so much time in discussion of the instrumentation. Let's see the next question. In of the following crystals, type 2 phase matching is obtained in. Now we have like what type of phase matching happens in what type, in which crystals. So let's see. Here I am writing the crystal, and here is the phase matching. Now let's write, first one is the KDP. Now for full form it is potassium dihydrate phosphate. Okay, it has a type 2 phase matching. The second one is KTP, which is potassium titanyl phosphate. This all I don't know why it is going every time. It has also type 2. written this 100 times. It doesn't want the potassium to be complete. Okay. So the next one will be, which we use mostly, third is, let's say, our BBO, which is beta barium borate. This formula is Ba2 whole 2. It has a phase matching type 1. Another which is used is LBO. What is LBO is lithium. So these are the type of nonlinear crystals which we use in such instruments. This is lithium triborate, B3O5. This also has a type 1. Fifth one is which is, and it has a 5% MgO. So this is lithium niobate. It also has a type 1 phase matching. So these are the common crystals. It is used as nonlinear crystals. So because we have seen that not all the crystal can give nonlinear optics, because the crystal should have high Chi2 susceptibility, that is a high second order susceptibility, and should be non-centrosymmetric. It should be non-centrosymmetric, should have at least one optical axis. So there are many more conditions for a crystal to act as a nonlinear crystal. So we have very few restricted crystals which is used as a used in the instruments, such instruments, and that's why they are costly also. So the question asked was, which one of the following crystal has type 2 phase matching? So the type 2, it's written over here only. Type 2 phase matching is obtained using the crystals KDP and KTP. So the option 1 and 2 are correct. It's an MSQ, so we can select both. So type 2 phase matching is obtained using KTP, potassium titanyl phosphate, and KTP, potassium dihydrate phosphate. Okay. So let's see the next question. The next question is about challenges in the second harmonic generation of an ultrashort pulse. Now, let me write an expression here. Is the intensity of the second harmonic. It is given by K So this is the intensity of the second harmonic which we get. So these are the different terms: constant, high second order susceptibility, coherence length, and this is the factor which comes from the mode locking thing, and this is the intensity of the our fundamental. So if we have, so for ultra short pulses, I naught is always high. I naught is high for ultra short pulses, but this is a challenging thing to get high I naught for the ultra short pulse. First thing is this one. Next is so it has spectral bandwidth. Spectral bandwidth means it is something like this. So this much is the spectral bandwidth. We say if this one is our 700 nanometers, but it will not be exactly 700 nanometers. This much will be the spread. So the ultra short pulses inherently have a spectral bandwidth which comes due to the mode locking condition. So, but this spectral bandwidth means that there are right, spectral bandwidth means there are so many wavelengths, and this implies that there are so many k vectors. There are so many k vectors. So, and delta k has to be 0 for each of them. Delta k equals to 0 is difficult to achieve. Is difficult to achieve for the entire band. That is the entire band. Okay, we need to get phase matching conditions satisfied for each wavelength. That is, phase matching should be satisfied for the entire band. Correct? And which is a difficult thing to achieve, right? So these two are the challenges if we are using ultra short pulses. for generating second harmonic. So answer to this question will be spectral width and this high peak power. Okay. So here I have given a example of what a phase matching means. So what does phase matching mean? When delta k equals to 0, and this phase matching condition we had seen in the previous session, that the refractive index of our fundamental should be equal to the second harmonic. That is, the phase velocity of the input and the second harmonic are equal, and lambda omega is equals to 2 times the lambda of 2 omega, the second harmonic. 2 omega is the second harmonic. So that's how the phase matching looks like. Even if the amplitude is not constant, we still have the fundamental and the second harmonic. They are relatively at the same phase at all points of time and distance. So the two waves maintain the same relative phase as they propagate. So it is shown here with this gray dotted line, that you can see that wherever this dotted line is there, the phase, the relative phase, that the maximum of this is matching somewhere with here of the second harmonic. The maximum of this is matching at exactly the same point as here, and as here. So the phase difference between the two waves is not changing. The phase difference is constant. But when the phases are not matched, and when the delta k is not 0, that is the phase of this minus the phase of this, the difference in the phases is not 0, then what happens is the physical situation is like this. So you see the maximum of this is matching with the minima of this. Here it is matching somewhere else. Here maximum of this is matching nearly to the maximum of this, and here also to the maxima. So this is the situation of where the phase matching is not happening. The fundamental and the second harmonic are at different phases as they propagate. So the condition delta k into L is less than 1 ensures that the two waves don't walk too far out of phase with each other before reaching the end of the second harmonic crystal. So as the thickness, L is the thickness of the crystal. L is the thickness of the crystal. So if this much is the crystal thickness, so suppose the second harmonic, here is the pump, the second harmonic gets generated, and from here the pump and the second harmonic both are traveling. So the pump is my red, and from here the second harmonic and pump both are traveling in the same direction. So as soon as they travel, they should be phase matched. So this is what is written here. The condition delta k into L should be very less than 1 ensures that the two waves don't walk too far out of phase. So this, I am denoting this situation as the out of phase, and if they are like this overlapping, then suppose they are in phase. They don't walk too far out of phase before they reach the end of the crystal. So before they reach end of the crystal. Okay, so the question 6 was this much only, that what are the challenges in creating the ultra short pulse. This was the figure, just I have kept this to show what is the phase matched and phase dismatched conditions. What does it look like physically in the wave picture. Next, we have two more questions left. The next question is about the difference in the passage of time of the fundamental and the second harmonic light through the nonlinear optical crystal is smaller than the pulse width, then what happens? Now let's do the derivation then. So the difference is given by this. This difference is given by delta t is equals to 1 upon c So the notations are self-explanatory that n is the refractive index and f stands for fundamental, sh stands for the second harmonics. So if we want the difference should be smaller than the pulse width, then so actually we don't want too much delta t because they have to for the wave packet to sustain. So that's why the question is asking about the delta t should be lesser than the pulse duration. So we want delta t smaller than the pulse duration. That is, the condition should be like this: smaller than the pulse duration or almost equal to 0. Almost equal to 0 is the best. So from this expression, if delta t is equals to 0, we will have dnf divided by d lambda f into lambda f minus dnsh by d lambda sh into lambda sh will be equals to 0 from the expression here. This one, equating delta t equals to 0, c is the constant. So we come to this expression. Now just do the shiftings, that is dnf by d lambda f into lambda f is equals to dnsh by d lambda sh into lambda sh. Now the relation between the wavelengths of the fundamental and second harmonic is that that lambda f is equals to 2 times the wavelength of the second harmonic. So you can put this condition here. So we will get 2 dnf by d lambda f. This lambda f, instead of lambda f here, we have put 2 times lambda sh. So this dsh divided by d lambda sh. Lambda sh will get cancelled on both sides. That is, the rate of change of refractive index with respect to the wavelength of the second harmonic should be twice of that of the fundamental. The meaning of this expression that rate of change of refractive index with respect to the wavelength for the second harmonics should be twice the rate of change of wavelength rate of change of refractive index with respect to wavelength of the fundamental. This is what is meant. So let's see what's given in the option. It's given dnf by d lambda f is equals. So we didn't get the condition like that. It is not equal. It is not equal. So it is unequal. Correct? So this option will be true. It is unequal. And now we have to see the factor dnf by. So we got the expression as 2 dnf by d lambda f is equals to dnsh by d lambda sh. So it is written then dnf is equals to, just transform this, dnf by d lambda f is equals to 1 upon 2 dnsh by d lambda sh. So 1 by 2 is the factor which will come here, which is in the second option. So the second option is also correct. Second option and the fourth option are correct for this question. Okay. So let's move to the next one. I think that one is the last question for this assignment. So the eighth question is, the optical parametric generation is reverse of some frequency generation, necessarily involves generation of two different colors, is less probable than the sum frequency generation, and does not conserve momentum. So let's discuss about the optical parametric generation, OPG. Now, what we used to do in the sum frequency generation, we were using two photons, signal, one was idler, and it used to give the pump photon, right? So So this is signal, this is idler, and this used to give the pump photon. So this was the some frequency generation. Now the reverse order is the parametric generation. Is the reverse process that one photon of higher energy splits to give two photons like this. So one photon which is of higher energy, it will split in two photons, and one is signal and one is idler. So this part, this is the reverse of this. So the first option for this question is obviously correct, that optical parametric generation is reverse of some frequency generation. First option is correct. But this process is a difficult process. There can be many combinations of omega s and omega I of the signal and idler, right? So suppose we have take example of the second harmonic generation. Suppose we have 5 plus 5. So 5 and 5 will give 10 only. But if we want to break 10 into two constituent, we can make combination of 2 8, 3 7. We can make combination of 5 5, 4 6. So there are so many combinations possible. And how do we decide that which one will come, or a mixture of all will come? So it's a difficult process because there can be many possible combinations, right? But there are some restrictions on this combination, which is given by the momentum conservation. Now first one was our energy conservation rule, which I wrote just now. Energy conservation, that omega p is equals to omega s plus omega I. But this does not give this gives many possible options. So energy conservation is, pictorially it can be denoted like this, that we have one omega pump and it can give omega s, omega p, sorry, omega I, idler. Omega s plus omega I. Right, now the momentum conservation, so this is that if this is the momentum of the pump, K pump, then the momentum of signal and the momentum of idler should match. So it's a vector sum rule that the momentum of the pump should match vector addition using the triangle rule. Ks plus Ki should be equal to the pump momentum. So because of this condition, due to this momentum conservation, we will have lesser number of combinations which are possible. Conservation of momentum condition. The number of combinations reduce because all combination will not follow the momentum conservation. The momentum of the signal and the idler photon will not match in all those combinations. So that's why we have a lesser number of combinations possible, but still the number of combination is more only. So the phase matching condition in this case is given by the last thing which I will tell today is this one. The phase matching condition is given by and this one is the wavelength, frequency, this one is the refractive index into frequency of the pump, and then the signal plus the idler. So this is the phase matching condition here, and the refractive index, how we choose that which combination of omega s and omega I will come. So this is chosen using by changing the refractive index, the ns and ni. If we fix ns, and ni, then there is only one combination, one pair of omega s and omega I which will satisfy this condition, right? This is fixed, this is fixed. If ns and ni can be controlled, then omega s and omega I will have to be only one particular pair which will satisfy this equation. And this refractive index is controlled by controlling the temperature. So refractive index is a temperature dependent thing. Okay. So temperature tuning is very important here. You have to tune the temperature, and also the angle tuning is there for phase matching. Angle tuning of the crystal is there. Now with angle tuning, we have to do the temperature tuning also here. So that's why this this reverse process becomes little bit difficult here. So the answer of the uh, question is optical parametric generation is the reverse of some frequency generation, which is true. Necessarily involves generation of two different colors. This omega s and omega I can be of same color as well. It can be exactly reverse of the second harmonic generation. So this one is not true. Depending upon the temperature and the refractive index, it can be same. Is less probable than the same frequency generation. Yes, it is less probable because here we have to take care of the temperature, the angle, the refractive index. It does not conserve momentum. No, this is false because momentum conservation happens here as well. So for this question, the answers are A and C. So I hope these answers are clear to you. And then we have come to an end of the discussion. So we have completed today's discussion of assignment 8, and I think we will have to discuss two assignments together in the last week, because we are like lagging behind 1 week, because the live session ends on, I think, April 24th. So we have to discuss two assignments together. The last two we will discuss at once in the last week. Okay, so next week we will be discussing the week 9th assignment. Okay, so I'm ending the session now.